So we'll begin with the chemical properties of alcohols, a part of which we had done yesterday. Okay. So we said that the chemical properties of alcohols can be studied under three headings. The first one is the acidic nature, where the cleavage of the, if I actually write it down for your briefed notes, if you want to make, here you can write down it is due to the cleavage of the ROH bond. Okay, that means the carbon oxygen bond. Under the oxygen hydrogen bond. Under this, we did three kinds of reactions yesterday, and the order of the strength goes as primary, then secondary, then tertiary alcohol. Okay. And if you look at the reactions that you had to do in this case, the first reaction was the acidic nature with a reactive uh, element, with a reactive, very reactive, or you can say just a reactive element like sodium. Okay. The next one that we did was the esterification. And in the esterification, you will also learn that it is the, when the ester is formed, okay, it is the oxygen of the alcohol group uh, which remains in the ester. It is not that the OH of the alcohol is lost. It is only the hydrogen of the alcohol is lost. And amongst the carboxylic group, the carbonyl carbon remains as it is. It is the OH of the carboxylic group which is given away. Okay. So esterification, maybe one or two examples regarding this, if we do, you will be able to remember that. And the third thing that we did was the reactions with RCOCl and of course with R, that is acid anhydride, that is RCOO, then you have a CO and an R. And of course in these cases we said the reaction is going to be carried out with alcohol in presence of pyridine, which is a weakly alkaline organic compound. Okay, today what we are going to do is the cleavage of the O and the carbon bond. That means this bond has to be ruptured. All right. And when this bond will be ruptured, obviously this group is going to undergo the substitution. Now, what is the order followed in this case? That is tertiary, secondary, and primary. Now, why is this followed? That I will take up when I begin with this topic, that why tertiary is the most reactive alcohol in this case. However, if its reactions with the HX is concerned, then we have to also remember that HI is the most reactive due to the larger bond length, then it is HBr, and then it is the HCl. Of course, HF does not show reactions under normal conditions. And under this, we will be doing the reactions with, of course, HI, this is one reaction. Then the other one that we will be doing is with phosphorus trichloride, phosphorus pentachloride, and of course, SOCl2. All right, thionyl chloride. This is also important reaction to understand. And then the third that we have to study here is that both the alkyl group and the hydroxy group are involved. All right, both the alkyl group and the hydroxy group are involved. And under this, you have to study the oxidation, you have to study the reduction, you have to study dehydration. Okay, so oxidation, reduction, and dehydration, we will study under that heading. And then after that, dehydration also is under like whether you are using alumina or whether you are using a hot copper tube. The primary, secondary, tertiary will show different reactions. So basically today we will be concentrating on this chemical property, that is the cleavage of the carbon oxygen bond. Okay. So if I start with this part here, then first we need to understand that why is it that the tertiary is more reactive than the secondary, which in turn is more reactive than the primary. Reactive in the sense that they undergo the reaction easily. Actually, this also forms the basis of the Lucas test. Lucas test is used for differentiating between primary, secondary, and tertiary. The tertiary react fastest and they give the required precipitate very soon. Secondary will give within 5 minutes, and then the primary, they do not usually give the precipitate with the Lucas test. So we'll take up that. let us start with the cleavage of the RCOH bond. Okay, now before I go into that, there is one thing I was talking about, esterification. And in your joint entrance exams also, they ask, because mechanisms are included, they ask that which one will be the compound formed when the certain set of acid and alcohols are taken for esterification. Now let us say I will keep the R group same because I want you to concentrate on the oxygen. Now let us say this is O and this is O and hydrogen. Okay, now let us say this is O16 and this is also O16. Okay, the alcohol with which it is reacting, if I show the alcohol, then let us say I will show the alcohol in blue, and the O in this case are remaining the same. The isotope of oxygen is O18. Okay, and this is made to react with the two compounds will react in presence of concentrated H2SO4. Now, what is the mechanism? Obviously, we did that yesterday, that the protonation of the OH group of the acid will take place, and then it is removed, and then this OH is actually going to attack the carbonyl carbon. So what is the product that you will actually get is written like this. Suppose you have R, C, double bond O, I will write the isotope of oxygen, and then it's going to be oxygen of the alcohol group, which will be 18, and an R will be formed. So this is the ester that you are supposed to get. Now in the multiple choice questions, they can give you, compounds like this: R, C, double bond O, 16, then O, 16, and then an R is given. Okay, or they will give both of them, they'll make it as 18. Or this, the carbonyl carbon can be made 18 and this can be made 16. So you have to be careful. Look at the reagents. The oxygen of the alcoholic group. Okay, Ananya is asking that why do we take the isotope of oxygen? I'm just trying to explain to you that after the mechanism, which oxygen will remain with the ester and which one will be given out. Okay, so here in this case, you see, I have taken oxygen 16 in the case of the acid, and in case of the alcohol I have taken it as O18. So this is going to be the correct product that will be formed, and not this one, because this 16 is actually from the acid, indicating that the oxygen of the acid only added up. No, it is the oxygen of the alcohol group which is actually adding up to form the ester. So this part you have to understand. So this is little things that you have to keep in mind. Otherwise, if you overlook this part, then selecting the right option becomes a problem. Because if you're sitting there for the marking of the MCQ questions, then you will think that oxygen though is supposed to be the same. So why is this 16 and 18? No, it is just testing whether you know the mechanism of the process. Okay, so that is how it will be there. You can also have a compound which will be given like, this is oxygen is 18, and this oxygen is also 18, and it is given as an R. This means that the alcoholic oxygen added up in both places. No, again, this is incorrect. So this one also will not be the option. So the correct option will be here. The fourth can be given, inverting that 18 and 16. So remember, the carbonyl oxygen comes from the carboxylic acid, and the O from the alcoholic group will add up to the carbonyl carbon, and that is how the reaction will proceed. Okay, so this was about esterification. Now let us come to the next part, that is the cleavage of the carbon oxygen bond as the next part of the chemical properties. Now if I look at this compound, this bond has to rupture. So in the case of alcohols, the structure is like this, and we just discussed the rupture of this bond, and we said that hydrogen can be given out easily as an H plus, because the oxygen hydrogen bond is polar. Now if you have these groups here, in this case, to support oxygen and strengthen the charge on the oxygen, then obviously it's going to have its effect on the rupture of the bond. Now if I am coming to the rupture of carbon oxygen bond, that is this one, then how do I look into the matter? You see, you have studied that primary, secondary, and tertiary carbocations, when they are compared, the tertiary carbocations are more stable due to the increased plus psi effect. All right. Why will there be a increased plus I effect? Because the three alkyl groups are electron pumping. So if I have a carbon, okay, this is all hydrogen, okay, and I take another one where I am going to write it like this: CH3, okay, CH3 and a CH3. Of course, there will be one which will be in between, that is a secondary, and this is an O and this is an H. Remember, the state of hybridization, the electronegativity difference between the carbon and oxygen is same, because we are talking about the bond between carbon and oxygen. But in this case of the tertiary carbocations, in the case of the tertiary or the tertiary alcohols, the alkyl groups always have a plus I effect. Okay. Now, when this bond has to rupture, carbon oxygen bond has to rupture, oxygen has to move with the negative charge, and carbon is supposed to develop the positive charge, because the bonded pair of electron will go with oxygen. Now, this will give rise to a carbocation. This will give rise to a carbocation. In the case of the first one, that is in this case, the carbocation that is formed is a primary carbocation, and in fact, it does not have any alkyl group attached to it. But in the case of the second one, it is this one, it is a tertiary carbocation. So when you have a tertiary carbocation, look at the the process here. If this is a tertiary carbocation, it will always try to neutralize its charge by getting some negative charge, and therefore what will happen, if this charge is stronger, it will not allow the oxygen to move out. Okay. But if the positivity of this carbon atom is kind of being neutralized, not neutralized, but kind of being lessened due to the electron pumping nature of the alkyl groups, then this carbon is happy because it's getting some electrons from within its own alkyl groups. So it will allow the oxygen to move out. That means it will allow the OH group to move out. And therefore, this becomes a good leaving group compared to when it is attached to only the single carbon atom. All right. And so what will happen is that in this case, when we are talking about a polar bond between carbon and oxygen, all right, electrons, as okay, Ananya says it has to be del positive and del negative. Fine, I'll write it here. But after it is rupturing, it is going to be, this is going to be positive and this is going to be negative. So what will happen is that due to the stable carbocation, the release of the OH group in the case of tertiary alcohol becomes easier. And therefore, the reactivity order of the primary, secondary, and tertiary alcohols in the case of cleavage of the carbon oxygen bond follows the order that tertiary is maximum, then is secondary, and then is primary. This also forms the basis of the Lucas test. All right. So now let's do the reactions related to this. Now, what are the reactions related to this? One thing you have to pay attention to is, like, suppose I am giving you this reaction C2H5OH. Now, this is a primary alcohol. Okay. This has to react with HCl. Please make sure whether the HCl that we are taking is the concentrated HCl or whether it is in the gaseous form. If it is in the gaseous form, then it is the hydrogen chloride gas. All right. Then this has to react, and in presence of, anhydrous ZnCl2. Now, ZnCl2 is used in the Lucas test also. So ZnCl2 and heating, it is going to release the OH and the Cl will take its place. All right. So H2O will be given out and C2H5Cl will be formed. Now, if you look at the conditions of the reaction, in the case of secondary alcohol, heating is not required. And in the case of tertiary alcohol, the reaction, just happens on it. I mean, it happens easily. All right. So this test where we are using HCl in the gaseous state, all right, HCl in the gaseous state in presence of anhydrous ZnCl2, all right, in presence of anhydrous ZnCl2, this test is called as the Grooves test, all right, or it is called as the Grooves method. It is called as the Grooves method. Okay. Now this is different than the Lucas test, because in the case of the Lucas test, the reagent is concentrated HCl and ZnCl2. All right, and ZnCl2. That is, in this case, in the first case, it is the HCl gaseous, whereas in this case, it is the concentrated HCl and ZnCl2. Of course, this is also going to be anhydrous, and you are going to take in the ratio of 1:1. Okay, and how will this method help us to distinguish between primary, secondary, and tertiary alcohol? If the Lucas reagent is added to the three alcohols, tertiary, secondary, and primary, taken separately in a test tube. Okay, you take three test tubes, and each of these three test tubes you add separately the primary, the secondary, and tertiary alcohols, and you add the Lucas reagent to it. It is observed that the tertiary alcohol immediately, it forms. The minute you add, immediately it is going to form the turbidity. The turbidity that is formed is due to the formation of the RCl that will be formed, the R being the tertiary group. And in the case of the secondary alcohol, it is going to take about 5 minutes for the formation of the turbidity to appear. And in the case of the primary alcohols, it may not appear only. And even if it appears, you have to leave it for quite some time. Only then it appears. So this forms the basis of distinguishing between primary, secondary, and tertiary alcohols using Lucas reagent. Now, what is the role of anhydrous ZnCl2? Can we not just carry it out by just using the HCl? No. Why? Because OH of the alcohol group, the OH of the alcohol group, this probably is not given in your book. If you want, you can make a note of it. The OH of the alcohol group is not a good leaving group. All right. Now, what does a leaving group? Leaving means LEAVING, not living. All right. It's a OH is not a good leaving group, but halogens, these are good leaving groups because they move out easily. The bonds are longer and they break up easily. So, what the anhydrous zinc chloride will do is actually, suppose if this is the ROH that we are talking about, it kind of complexes with the oxygen. So, this is del positive and sorry, this is going to be del negative. So this oxygen is del negative. Actually, what happens is that the OH, the ZnCl2 will actually complex with this, and when it is going to complex, it is going to form, let me remove this charge first, it is going to form ZnCl2, it's going to attach here because it has the empty d orbitals. So this is working as a good Lewis acid. Okay, and what it will do is it's going to complex with this in presence of Cl minus. The Cl minus is coming from concentrated HCl. This Cl minus, let us say, is coming from concentrated HCl. So what it does is, it is first going to complex and form this compound, and because it is ready to accept the electrons from the oxygen in its empty orbitals, what will happen is you get an R, O, and an H, and this kind of develops a positive charge, and ZnCl2 attaching itself here kind of develops a negative charge, and this on presence of the Cl minus further changes into R Cl. Okay, it's going to form R Cl, and it's going to form ZnCl2OH. All right, this is a complex compound that is formed. This is a complex compound that is formed, and further on, this is when treated with, it is treated because the acid is there. There is an H plus from the acid. This is going to react with it, and it is going to regenerate ZnCl2, and of course water will be given out. So the role of anhydrous zinc chloride is basically to help the OH group to come out of the compound easily. And in what will happen if you don't take anhydrous ZnCl2, maybe you will not be able to distinguish between the reactions because it may take different time. So it is usually the lower alcohols which are capable of showing this kind of a Lucas reagent test, and you are able to differentiate between a tertiary, secondary, and primary. Okay. When I said lower alcohols, what I meant was that the primary alcohols usually will not give the test. So it's easier to distinguish them from the tertiary alcohols. So this is what is there about the Lucas test under the heading of the carbon oxygen cleavage. Okay. Now, the next important thing that you have to, the next important reaction that you have to study is the reaction of the ROH with, I will put a slash and write PCl3, PCl5, and SOCl2. Now, please, you all have to remember these chlorides of phosphorus, phosphorus trichloride, phosphorus pentachloride, and thionyl chloride, that is SOCl2. These are important reagents for substituting the OH group with a halide. Okay, wherever there is an OH group, if it is to be substituted, then you can use any one of these reagents. You will come across this in acids also. The OH group of the carboxylic group, OH, also gets replaced, you know, by when you are using phosphorus trichloride or phosphorus pentachloride or thionyl chloride. Okay, what will be the products? See, I'll show you. If you take ROH, first one let us take, if I take, R stands for any alkyl group. Here, in this case, let us say R we are taking as an OH group. Okay, this is made to react with PCl3, the lower chloride we are taking. When this is made to react with PCl3, then what you are going to get is an RCl. Okay, RCl, that is an alkyl halide, will be formed, and along with this H3PO3 is formed. H3PO3 is formed. Now, is this balanced? It doesn't look balanced because 3Cl is there. So you will have to put a 3 here. And if you put a 3 here, there has to be a 3 here. And I think it's balanced now. Yeah, okay. So this is what is happening. So you are getting an RCl and you are getting an H3PO3. All right. Phosphorus acid. Then next, what you are getting is the second one. ROH. Okay. Treat this with PCl5, phosphorus pentachloride. Okay. What will happen in this case? In this case, 3 products are obtained. One is the RCl. Then the next one you get is POCl3. Okay. And of course, in the next one, you will get an HCl. H has not come out anywhere. Okay. So you will get an HCl. Okay. Now you see in this case, 3 products are obtained. RCl, POCl3 and PCl5. Are the chlorine balanced? Yes. 3, 4 and 1, 5. Balanced. Phosphorus is 1, oxygen is 1, and so all set. So with PCl5, 3 products are obtained. With PCl3, 2 products are obtained. And the third one is treating it with ROH is to be treated with SOCl2. Now you see, when I'm taking SOCl2 and I have to use a pyridine molecule here. So if I'm using a pyridine, then try to understand, again, it's the weak alkaline nature of pyridine that is used here. The products that we are getting is RCl plus you will get HCl, which is going to be gaseous, plus you are going to get SO2. Okay, so you have put an arrow upwards indicating that the 2 products other than RCl are gaseous. So sometimes they ask a question, amongst the following PCl3, PCl5 and SOCl2, which is considered to be a good chlorinating or which is a preferred reagent for introducing the chlorine group? You have to look at the reagents and you will see reactions and see that in the case of SOCl2, the byproducts are gaseous in nature. Now, because they are gaseous in nature, the product obtained is all by itself. That is, RCl will be obtained because the other 2 being gaseous will be given out. So we don't have to, carry out any further process to remove or separate RCl from other products. But in the case of PCl3 and PCl5, you find that the products are POCl3, HCl, and in this case also it is a H3PO3. So RCl will have to be separated from POCl3 from H3PO3. That is why thionyl chloride is considered to be a more favorable reagent for displacing or for substituting OH with a Cl group. All right. So one thing is certain, that all of them are going to form the haloalkanes, and it is the case also. Obviously, again, the reaction, if at all there is any comparison that is asked, obviously the tertiary will react most easily, then the secondary, and then the primary. Okay, so these were the reactions you had to do under the cleavage of carbon and oxygen bond. The last one that was there, the third set, was reactions which involved both the alkyl groups as well as the hydroxyl group. Now, this was very easy to understand, because you see, if you have been given an alcohol, okay, let us say I'm talking about CH3, CH2OH, okay, what will happen if this is oxidized? All right, this can be easily oxidized by using any of these oxidizing agents like potassium dichromate in presence of dilute H2SO4, because that's a good um, uh, oxidizing agent. So in presence of K2Cr2O7, I can either write, or you can remember, that is K2Cr2O7 in presence of an acidic medium. It is first going to get oxidized to RCHO, that is the aldehyde. What happens is, actually in this case, the hydrogen, there is removal of 2 hydrogen. This, on further oxidation with the same reagent, if you don't remove the compound at this stage, or you do not use any other reagent, like if you use Collins reagent, then the reaction will stop at RCHO along with this. But if you don't use, then the ultimate oxidized product that you get is the acid, that is the RCOOH. One second, let me just change this to CH2 and this to CH2, so that I can explain to you that in this case, the compound that is formed is containing the same number of carbon atoms. There are 2 carbon atoms in the ethyl alcohol, 2 carbon atoms in the aldehyde, and 2 carbon atoms in the acid. This is ultimate, the complete oxidation. Further on, if it is heated and burned, then of course it gets converted to CO2 and H2O. But as far as the oxidation process is concerned, using potassium dichromate acidified, then this is what you get. All right. Now, if this is about the alcohols of the primary alcohol, is it that the secondary and tertiary will also behave in the same manner? Let us see what is the difference now. In the case of, this is the primary alcohol that we considered. Now let us consider the secondary alcohol. So I will take H3, okay, CH3 or CH3 here. I will take C, all right, there is an H, okay, there is an H, okay, 1, 2, I have to take one more carbon atom. Let me make this as CH3. Okay, this is H and this is OH. So this is a secondary alcohol. So if this is a secondary alcohol and it has to undergo oxidation, in the first step of the oxidation, you see it is the hydrogen which is given out. So it is actually the loss of 2 hydrogen atoms. Loss of hydrogen is oxidation. So let us say these 2 are given out. So what you are left with is a CH3, C double bond O. So you get a ketone. What you get is a ketone. Here what you got was an aldehyde. Just observe that carefully. So you get a ketone. Now when this ketone is subjected to further oxidation, see, there is no way that this oxygen can form an acid, because it has to break up then. So when it breaks up, when it is going to kind of undergo further oxidation, then let us say it breaks up. So if it is breaking up from anywhere of these compounds, you are going to get a CH3, all right, and a COOH. That is, the carbonyl carbon is going to take up an OH, and of course the CH3 group gets converted into CO2 and you get an H2O. Meaning to say that On further oxidation, it is converting into CO2 and H2O, and you are getting an acid also. But this acid that is obtained here is containing one carbon atom less than the product with the compound you started from. So the acids formed in the case of secondary alcohol contain less number of carbon atoms. It is going to contain less number of carbon atoms. But if I talk about a tertiary alcohol, then what will happen? It is all going to be CH3, CH3 and a CH3, and this is going to react with an oxidizing agent. Again, this does not undergo oxidation easily. Why? Because obviously the bulkiness is there and the nature of the tertiary alcohols. Hence it is not oxidized easily by KMNO4 solution, but it can be readily oxidized if you are using acidified potassium dichromate. That is, here we are using the same, but what I'm saying is that the oxidation of the primary and secondary is comparatively easier. The tertiary does not usually undergo oxidation so easily, but at the first step only what will happen is that it is going to convert into, you see, if this carbon has to form the carboxylic group, it has to give up one carbon atom. So it is going to be CH3, C, CH3, and you will get a double bonded CH2. So first there is elimination that is actually taking place, and after that what will happen is it will convert into CH3, C, CH3. This carbon atom here is going to take up the oxygen, and this is going to be lost to form a CO2, and of course H2O will be formed because it is undergoing oxidation. So that is the thing. Again, in this case, you see, you started with how many carbon atoms? 1, 2, 3, and 4. 1, 2, 3, and 4. And the ketone that you are getting is with 3 carbon atoms. Okay. So that is it. And of course, if this is reduced further or oxidized further, if the oxidation process continues further, then the ketone will get oxidized to acid with still one carbon atom less. So you will get an acid again containing 2 carbon atoms. Therefore, 2 carbon atom less numbers will be found in the acid that is obtained as the ultimate product. So this is about the oxidation process. Okay, so primary, secondary, tertiary, just remember primary forms acids with the same number of carbon atoms. Secondary alcohols will form carboxylic acids, which will have lesser number of carbon atoms than the parent alcohol. And of course, the tertiary alcohols also will have. Miss, is the reaction with aldehyde stable or ketone is stable? Okay, just 1 second. All right, she's asking that is the reaction with aldehyde stable or ketone is stable. You need to, elaborate a little on this, Ananya, because I don't understand what you are asking for. Aldehydes and ketones, they come in between. They are one of the intermediate products that are being formed. Ultimately, it is forming the acid. And we are focusing on the acid that is formed is containing less number of carbon atoms. In case of tertiary alcohols, the number of carbon atoms formed are still less. In secondary alcohol, lesser number is there, but in case of this, it is still less. Okay. And then the next is, of course, the dehydration that reduction we had to do, right? So the next that we will do is the reduction. Children, remember, in the case of reduction reactions, okay, alcohols, if they are reduced, they have to give what? If alcohols are reduced, they have to give alkanes. HI and red phosphorus are one of the most important reagents. If I have to reduce this, let us say if I'm talking about C2H5OH, okay, if I treat this with HI, okay, in presence of red phosphorus, right, which is a kind of an ultimate reducing agent, which will actually reduce any compound, all right, to the alkane state. That is, you will get C2H6, all right, and of course, plus I2 will be, so I'll have to use a 2HI. It is going to form an I2, and of course, what is the other product? It will form H2O. Okay, so this is one reduction process that you have to study. And in the dehydration process, okay, the dehydration we'll do, probably that's the last part for today. The dehydration process. In the dehydration of the alcohols, obviously in standard 10 also you studied the preparation of alkenes, where you can obtain alkenes by dehydration of alcohols or dehydrohalogenation of alkyl halides. Okay, so when it comes to dehydration, uh, what are we talking about? We are talking about a loss of water molecule. Okay, now when alcohols are dehydrated, there are two things you have to keep in mind. One is the temperature at which the dehydration is going to occur. Okay, all right, Ananya, you have a question. Is primary alcohol reaction stable or secondary alcohol reaction stable? Um, Ananya, I don't, which one is more preferred? That is a better question than asking that which one is stable. The question is not about being preferring which reaction. It depends upon what reagent has been given to you. It will depend upon what is the reagent that is given to you. So if the primary alcohol is given, you have to begin with that. If the secondary alcohol is given, you have to begin with that. And the product obtained, you should know what you are going to get. The preference will come only if you have a choice as to which alcohol to start with. But in the question, if it is saying that a primary alcohol is undergoing oxidation, then what will be the product? That you have to understand. Okay. Now coming next to the dehydration part. So we were saying that a few things we have to keep in mind, that how does the dehydration occur. So we were saying that in the case of yes, Sananya, welcome. If we are talking about dehydration, we said, see, there are two ways a molecule of ethyl alcohol can undergo dehydration. I'm taking the simple, you cannot have a dehydration in case of methyl molecule, because after that only carbon will be left. But if I'm talking about ethyl molecule, let us say these are the hydrogens. Okay, these are the three hydrogens. Then you have a carbon, you have an OH, and you have an H, and you have an H here. When this is supposed to undergo dehydration, either the dehydration will occur between two different molecules of ethyl alcohol, or it will occur within that same molecule of ethyl alcohol. That will depend upon the temperature. Now, if you are using a higher temperature, usually if a temperature of 170 degrees Celsius is mentioned, okay, then what happens is, I used to remember the reaction like this, that if the temperature is high, the molecule does not need another molecule to, give out a water molecule. It gives out a water molecule from within itself only, and therefore what will happen, let us say this HOH is given out. Okay, OH from here and OH from here, and H from this carbon is given out. And of course, the compound that is formed is one hydrogen, double bond, carbon, a hydrogen, and an hydrogen. So an alkene is obtained, and of course, a water molecule is given out. But if the temperature conditions are less, if it is being carried out at a lower temperature, that is 140 degrees Celsius, this you will study in the ether chapter also, you will find that between two molecules, this was intra dehydration, that is, a molecule of water was lost from within the molecule. But when you are going to take two different molecules, in that case, then what will happen is that an OH, let me show you, CH3C, let us say this is H and an H, and this is an OH. Another molecule has its H, O, and then it has an H and an H, and see, they are both same molecules. Okay, then in this case, a water molecule is lost between these two. Actually, it goes through the process of forming a protonated alcohol, and then after that, the in presence of the acid, because all this will always be carried out in presence of a dehydrating agent, and the dehydrating agent used is concentrated sulfuric acid. Okay, so in this case also it is concentrated sulfuric acid. So you know that dehydrating agents will pull out the elements of water. So H2O is given out here between the two molecules, and therefore the compound that is obtained is actually CH3, CH2O, and then you have a CH2 and a CH3. So an ether is obtained. So if the temperature is around 140 degrees Celsius in presence of concentrated sulfuric acid, it gives ether. But if the temperatures are high at 170 degrees Celsius, then it is going to form the alkene. And remember the dehydration of the secondary or the tertiary alcohols. Let us see what happens in the case of secondary. You have already done the Sedzef rule. If you remember, or if you can recollect the Sedzef rule, you will know that in the case of the Sedzef rule, the more substituted alkene is the major product. So if I have an alcohol like this, okay, let us say we have okay, you have an OH here. I'm just taking the carbon skeleton in this case. So if you have a uh, OH in the second position, this is lost, fine. But from where should the hydrogen go? From the adjoining carbon atom, whether it is going to be this one or it is going to be this hydrogen or this hydrogen is the question. Okay, so let us see what happens. If this is hydrogen 1 and this is hydrogen 2, let us say in the first case, the first hydrogen is given out. Okay, first hydrogen is lost. So in that case, the compound obtained is going to be C double bond, and this is what you will get. But if it is the second hydrogen that is lost, okay, the second hydrogen that is lost, then the compound that you get is a 2-butene. So this is the major product. All right. According to the Sedzef rule, 2-butene will be the major product. What does the Sedzef rule tell you? That whenever there is an option for the molecule to lose hydrogen and form an alkene in the case of alcohol, or in case of dehydrohalogenation also, the preferred product is a more substituted alkene. So which one is a more substituted alkene? In this case, you see this is having 2 hydrogens and this is having 1 hydrogen, and these are all having 2. So in this case, only 2 hydrogens are there. So consider the carbon-carbon double bond. Around the carbon-carbon double bond, the less is the number of hydrogen, that is the preferred product. Okay. So in this case also, since the doubly bonded carbon atoms have 1 hydrogen each, it is going to be the preferred product as compared to this one. This is called as the major product, and about 80% of this is formed. We cannot rule out the possibility of the formation of this compound. It is also formed, but of course, the 80% is the major product that is formed. Again, the ease of dehydration of alcohols will follow the same order, that is tertiary, secondary, and primary. Okay, this is the order that is followed. And if you take a tertiary alcohol, in obviously there also the OH and the H from the adjoining methyl group or the alkyl group will be lost, and a alkene will be obtained. So that is the thing that you have to study today about the different kinds of properties of um, alcohols, that is primary, secondary, and tertiary. The other dehydration methods that are used are you can use alumina, that is Al2O3. In that case, again the temperature will play an important role. At 240 degrees Celsius, if you are passing the alcohol through alumina, then in that case an ethyl is formed. However, at a higher temperature, an alkene will be formed. And there is one more method by which you can differentiate between primary, secondary, and tertiary alcohols, but you will have to carry out further tests to identify them. That is passing the alcohol vapors through hot copper tube, that is copper at 573 Kelvin. Okay, if this is taken and primary alcohol is passed through this, then you will get an aldehyde. Okay, and if you are taking a secondary alcohol, then you will get an aldehyde. So this is the sorry, ethyl alcohol from the other alcohols. That is the iodoform test. Okay, that is the iodoform test. What is this iodoform test all about? If you take C2H5OH, all right, in the lab also you have done this. You will do this if you get to see the lab again. So this is 6NaOH. All right. These two will form sodium hypohalite. This is going to give you a yellow precipitate of CHI3, that is iodoform. Yellow precipitate of iodoform is obtained. Of course, the rest of the thing is going to be CH3COONA. This we will be taking up again in the forthcoming chapters when we do aldehydes and ketones, because it is an important test in the case of aldehydes. Okay, because this test, iodoform test, is very important. We will be dealing with this in the aldehyde chapter also. So ketones also. So this is all of that you had to do about the alcohols. Then the conversions of interconversions of alcohols. That part probably I will discuss in the next class. So the next class we'll have the interconversion of alcohols, and we'll touch the. I will try to finish up with the phenols. So now, since Monday is a holiday, I will get to see you on Thursday. So we connect again on Thursday for the class. Is that okay with all of you?
Yes,
It's
miss.
already okay. I hope today's you all have understood the
Yes.
whatever we have done. Yes?
Yes, miss.
Okay, I'll try sending the recording to Rishika, because she said she won't be able to connect, and evening I wasn't free at around 4 o'clock because of Sunday. Something else was scheduled. Okay, so that's it, I think.
Thank you, miss.